All right, welcome back in, Organization Architecture students. We're going to dive on into our second combinational circuit video. We started off with thinking about, well, we want to do addition with 2 bits. Well, it turns out that once you have 2 bits and you have a carry bit, then if you're adding a sequence of bits, then you actually really need to add 3 bits at various points. And so you can think of each of these as a separate set of addition. So what happens if you're adding 2 numbers that have zeros in them? At the current index you're adding, and you had 0 carry bit. What happens if you're adding 2 numbers and you have a 0 for the first number, 1 for the second number, and a 0 carry bit, and so on. So we're kind of assuming that we already kind of have a carry bit coming in along the top row here, and then these might be 2 numbers that we're adding, but we're doing this 1 column at a time, right? So if we think about each of these columns individually, if we add a 0 plus a 0 plus a 0, we get a sum of 0 and a carry of 0. In fact, running all the way across this first set, it's going to match exactly what we did up above, because that's what we did. That we're assuming there's a carry bit of 0 for the 2-bit addition, so we can fill in these the same way. Right. So 0 plus 1 is 1. 0 plus 1 plus 0 is 1. 0 plus 1 plus 1 is 0. Carry 1. Now the part where it diverges is when we start looking at, well, what if we had a carry bit in this particular column? So if we were adding 2 zeros but had a carry bit of 1, we get a sum of 1 and a carry of 0. If we had a carry bit of 1 and we're adding a 0 and a 1, then we get 0 carry 1. 1 plus 1 plus 0 is 0 carry 1. And 1 plus 1 plus 1 is 1 carry 1. So we end up with this nice little set of results here. And so we could, if we wanted to, set this up with 3 input switches and 2 output light bulbs, and just use and or NOT gates, and make this truth table setup. So if A is 0, and B is 0, and C is 0, then sum and carry are 0. Of course, we only would need to wire up where like sum is 1 and carry is 1, but it still gets really complicated. And if you try to draw this from scratch, just like many of the circuits that we're going to do in the project, if you try to do them completely from scratch, you're going to have a hard time. It's going to be a huge amount of work and a ridiculous number of ANDs, ORs, and NOT gates. On the other hand, we can go back and look at the work we already did. Look for a similar problem. So a similar problem we did was solving this half adder. I called it a half adder. That's why, because it's only about half of the addition that you have to do. If you look over here, we basically did adding half of the possible options we have for adding up 1s and 0s when we're doing binary addition. And now we would really like to do the full adder, which is how lets you cover even when you have a carry bit. So for our half adder, it works. It does all its logic. And to make the full adder, it actually maybe makes sense to use the circuit we created. So I'm going to go ahead and use the little integrated circuit we already made, and I'm going to tie it in with some other things. So I'm going to bring in a new toggle switch, call the next toggle switch B, call the next toggle switch C. And we'll put labels next to them so we know which one's which. A, B, and C. And as we were just kind of discussing and talking about here, we need 2 outputs. So we need the sum bit, because even when we're adding 3 values, it's still just only a sum and a carry. So I'm going to put those in there as well. And we'll go ahead and put some labels. So now, if we want to use our half adder here, another reason it's called a half adder is that you really need 2 of them to do full addition. So I'm going to pull in another half adder, and we'll have to think about how we want to wire these. So the idea here is that we want all the math to work. So let's start by just doing a half addition of A and B. So let's do what is A and what is B. So let's pull those on in. All right, so if we add A and B together, we could get a sum bit and a carry bit. So let's flip back over to our spreadsheet for a second. So imagine that A and B are the first 2 things here and C is the bottom one. the question is, what do we want to carry through, and how do we keep working on this addition? And actually, let's look all the way across. So if we have A's and B's together, and all the sets across here, if we add up and we have a sum that's 1, that could change depending on this last bit. It could change from a 1 to a 0 or 0 to a 1, and so things could still change. If we, however, it's worth noting, have a 1 and a 1 added together, then these are the only two scenarios where the carry bit turns on. And if the carry bit turns on from our half adder, well, then the carry bit turns on in our full adder. So we can tell one thing really important here, which is that the carry bit from our half addition, if it's a 1, will reflect what the carry bit will be in the final addition. So if we do this half adder and I have a carry bit, it's very possible that that carry bit could allow our final carry bit to turn on. In fact, we can guarantee it will. So if I wanted to, I could wire that here. Now, we're going to have to edit this in just a minute, but it's a good place to start if you can recognize that a carry bit in our half adder means we have a carry bit in the full addition. However, what's the sum and what's the carry, we can't actually tell just from these two, or at least the sum. Actually, we can't tell anything for certain just from these two. Right, if we add 0 and 0 and 0, then the sum bit's 1. If we had 0, 0, 1, then the sum bit's... Sorry, if we had 0, 0, and 0, the sum bit is 0. If we had 0, 0, and then add a 1, the sum bit is 1. In fact, for every combination of 1 and 0, we could have a totally different sum bit. However, if we carry that sum bit into the next addition, then we can more accurately predict what will happen. So we could take the sum bit from this and carry it in as an input to the second half adder. So we could say, all right, well, the sum from my first one, we have a sum bit that's a 1, but then if we add it to another one, we might end up with a sum bit that's a 0. In fact, we need to add the result of our first set of math to the result of our second set of math. So if we add these two together, well, now this all together will give us the correct sum bit. So let's make sure this checks out here. If I had a 0 and a 0, then the sum bit of the 0 plus 0 is 0. And if I add a 0 to it, the sum bit stays 0, and that is our actual final sum bit. If I add a 0 and a 0, and then I add a 1, if C is 1, let me write out here A, B, C. Right? If I have 0 from A and 0 from B, then the sum bit is 0. So we then add 0 and 1, and that gives us a 1 carry 0. So that works out well. If I go A is 0, B is 1, then the sum of this is 1. And 1 plus 0, the sum is still 1. And so sum stays 1, carry stays 0. So if we take the sum of the first two bits and add it to the third bit, then our sum and carry bits will work out correctly. The only trick being here is it's 1 plus 1. And so if we have 1 plus 1, we get a sum of 0, but 0 plus 1 gives me a sum of 1. So all the sum bits work out if we add the sum of the first two plus the third bit, then that tells us immediately what our sum is. But then this becomes the question, well, what about the carry bit from our second addition? If it's a 1, then we definitely have a carry bit, but what if we already had a carry bit, then this carry bit might be 0, and we might still want a carry bit. Turns out that if you actually really think through the logic on this, and I'd encourage you to pause the video and think it through and see if you can find a way of thinking about this that works for you. What we really want is that this carry bit, this final carry bit, is really, if we get a carry from our first set of additions or our second set of additions, then we overall have a carry bit. That is a 1. So what we actually need in here is an OR. And so if I carry from the first addition, if I have a carry bit, or if I have a carry bit from the second addition, I kind of wired this to a wonky terminal here, but that's all right. We'll just stick with it. Or if I carry this through my second addition, then that means that overall my addition has a carry bit. So it turns out that all you need to do full addition is take two half adders, run the sum of the first half adder into the second one, in addition to the third bit that you're adding. And then the sum of all three of these is the sum bit, and the carry bit is either a carry from the first addition or the second. So we can check out the math real quick before we end this video. 0 plus 0 plus 0 is a sum of 0, carry 0. That checks out. 1 plus 0 plus 0. See, we get a 1 from the sum from the half adder. 1 plus 0 is 1 with a carry of 0. We end up with a sum of 1 and a carry of 0. So 1 plus 0 plus 0 is 1, carry 0. That checks out. 0 plus 1 plus 0, 1 carry 0. 0 plus 0 plus 1, 1 carry 0. So all those check out. Now I can go 1 plus 0 plus 1 gives us a sum of 0 and a carry of 1. That checks out. 1 plus 1 plus 0. 1 plus 1 plus 0 gives us a sum of 0 and a carry of 1. That checks out. And then 0 plus 1 plus 1, sum of 0, carry of 1. That checks out as well. And the very last combination we have to check is 1, 1, 1. And that gives us a sum of 1 and a carry of 1. So the math on all this checks out. And we get our sum and carry bits, and now we have a full ladder.